When we talk about a function being continuous, what that means in simple language is that there is no break in the graph. So if there is no break in the graph, we have to think about, well, what would actually cause a break in the graph? There are three main types that you can actually have. So one type would be if you have a graph that has a hole in it. So something along the lines of here. That causes a break in the graph because you're coming along this function and then all of a sudden you get to a gap in the graph. Another type of break in the graph would be what is called a jump discontinuity. A jump discontinuity is where the function comes along and then it suddenly reaches a point where it jumps down and arrives at a different y value before continuing forward. This is also called a limit that does not exist due to differing behavior at this particular x value here. The third type would deal with if you have an asymptote on the graph. So I'm just going to draw a graph that has a vertical asymptote. So I could have something along the lines as this function here. And notice there's a giant break in the graph when I arrive at this vertical asymptote because this side is not connected to that side. Now, when we actually want to discuss the definition of continuity, in calculus, the definition is actually a three-part definition. We call that the three conditions of continuity. And we're going to go through each of these three, and I'll discuss what each one actually means as we go through them. So the first step, or the first condition of continuity, is that f of c is defined. Now, when we talk about f of c, that is the function value, or the y value, at x equals c. In other words, what this means is I have to have a point at x equals c. In other words, on your graph, you would have to have a closed dot somewhere along x equals c. You can't just have a hole or an asymptote or something like that. There must be a closed dot or a solid point at x equals c. The second condition is that the limit as x is approaching c of f of x actually exists. So in other words, the function actually has to connect from both sides. And we'll see an example of this in a moment when I actually sketch out different examples. The third and final condition of continuity is that once you have your point, f of c, and you have your limit, they must actually equal each other. So the limit as x approaches c of f of x must equal f of c. In other words, the point, the solid dot, must actually be in the same location as the y value, which is the limit. So here's an example of what I'm talking about. What we want to look at is a graph, and on this graph, we're going to determine, is this function continuous or not continuous? And if it's not continuous, what's the first condition that fails? There may be more than one reason why it's not continuous. We just want to talk about the first reason it's not continuous. So here's my graph, where I have a hole at x equals c, but it's connected everywhere else. So in terms of the continuity, there's a break in the graph, so I would say this function is not continuous, and I'm going to abbreviate continuous. And if I'm trying to determine the reason why it's not continuous, I have to go through the three conditions. The first condition said f of c is defined, meaning I have a y value at x equals c. Well, at x equals c, all I have is a hole. I don't have a y value here because it doesn't exist on the graph. So the first condition that fails, and actually the only condition in this case, would be number 1, and that is what is causing this function to not be continuous. Here's another example. Let's say I have a function that comes in and it does something like this. It's connected with a hole, just like I had on the previous example, but my point actually is up here at x equals c. So this function is definitely not continuous. We can see a break in the graph where we have that hole. And if I go through the three conditions of continuity, condition number 1 says that the point has to exist. Well, I do have a point right here. This value, whatever that y value is right there, that is f of c. So number 1 is true. The second condition said that the limit had to exist. Well, notice because it's connected on both sides, the limit is the y value this function approaches from the left and from the right. They both connect at the same y value, so even though there's a hole right here, the limit does exist. But then my third condition says the value of the limit has to equal the value of the point. Well, the point's way up here, and the limit value is down here at whatever this y value is. So condition number 3 would be the first one that actually fails to make this function continuous. So then with my third example, let's say we have a function that does something like this. It comes in from the left side with a solid point there at x equals c. C is just a random constant number. Then it has a hole down at the bottom and continues from there. Well, definitely I see a big break in the graph, so this is not continuous. And if I go through the 3 conditions of continuity, the first one says f of c exists, so at x equals c, I have the function value up here at this y value, that's where the point is located. Condition number 2 says the limit has to exist. Well, from the left side of x equals c, I'm at this y value. From the right side, I'm down at whatever this y value is. A limit cannot have 2 different y values as its answer. So remember, when a limit has it looks like it has 2 different y values, that limit does not exist due to differing behavior. So because the limit does not exist, condition number 2 is the first one that actually fails. Now when we talk about a function being discontinuous, that means not continuous, we have 2 different types of discontinuities that are possible there. We have what is called a removable discontinuity and also what is referred to as a non-removable discontinuity. A removable discontinuity means I went to the graph and I just removed one tiny little point from it, and that's what caused the break in the graph, which caused the graph to be not continuous. So if I'm removing a single point, I am leaving a hole on the graph. So a non-removable discontinuity would be a graph where it just comes along, has a hole, and then it keeps going. Whereas a non-removable discontinuity deals with a much bigger type of break in the graph. So another type of break in the graph that's bigger than a hole would be what we call a jump discontinuity. This is where the function actually jumps y values. So you would have to have a graph that came in to one y value and then suddenly jumped down to another y value. With limits, we refer to this as differing behavior if a limit did not exist. The other type of a non-removable discontinuity would be a vertical asymptote. And that's because on a graph with a vertical asymptote, you have one portion of the graph on one side, the other portion on the other side, and that causes this big gap or break in between the two, what we call branches of the function. So let's look at a couple different types of graphs that have different types of discontinuities, figure out where they're not continuous, and then name if it's a removable discontinuity or a non-removable discontinuity. To begin with, we're going to look at f of x is equal to 1 over x. This is one of your parent functions. So you should recall that that is graphed in the first and third quadrant with both a horizontal asymptote and vertical asymptote at 0. And so definitely this is not continuous. And in terms of the x values where it's not continuous, I would say it is not continuous at x equals 0. And that is due to this vertical asymptote that's right here in the middle. And if you recall by the definitions, a vertical asymptote is a non-removable discontinuity. So let's look at another one. With this one, I'm going to look at f of x is given by the rational function x squared minus 1 over x plus 1. Now, with a rational function, notice I can actually simplify this if I factor the numerator and cancel it out with the denominator. So I have difference of squares in the numerator. This will allow me to cancel the top with the bottom. When you cancel the same factor from the top and bottom, that actually forms a hole on the graph. And you can find the location by setting x plus 1 equal to 0. And so your hole is located at x equals negative 1. So if I was to graph this, we would have a hole at x equals negative 1. And I would be graphing the remaining portion of the rational function, which is this x minus 1. Now that has a slope of 1, y-intercept of negative 1. And so my hole, if I plug in negative 1 in for the x value here, would be located at negative 1, comma negative 2. And then I'm just graphing the linear function x minus 1. So a line with the slope of positive 1 going through y equals negative 1. So this is definitely not continuous, and I would say it is not continuous where the hole is located, which is at x equals negative 1. And a hole is what we call a removable discontinuity, because that's where we went to the graph and all we did was just remove that one little point, and that caused the break in the graph. So that would be the different types of discontinuities you could have, removable and non-removable, and also the definition of continuity based on the calculus definition.